Hello, my name is Brady Nicol, and this is my presentation on the Mersenne primes and the perfect numbers. So the Mersenne numbers are numbers of the form 2 to the n minus 1, where n is any natural number. They are named after the mathematician depicted on the right. Excuse my pronunciation, but his name is Mersenne. He asked questions about their primality. So whether these numbers were prime and how often they were prime. And so the Mersenne primes are just the Mersenne numbers which happen to be prime numbers. So if I list the first 5 here, you can see that they don't include all the primes by any means, right? There's quite a few missing from there. 5 is missing, 11 is missing, and so forth. But we can also notice that they grow really big, really fast, right? 8,191 is quite a bit bigger than 127, and so forth. And if we list the next 5, you can see they grow enormously large, right? That number on the right is 19 digits long, and that's only the 10th Mersenne prime. So there's a very interesting pattern amongst the Mersenne numbers and the Mersenne primes. If you list the first let's say, Mersenne numbers, and you cross out all of the composite numbers, so and 1, of course, because 1 is in prime, that will leave you with the Mersenne primes, right? Because these are all the non-composite Mersenne numbers. If you look at their exponents, you see that it includes all of the prime numbers up to that point, of course, which is interesting. And it's not immediately obvious why that would be true. And so a natural question would be, well, what about 11, right? What about 2 to the 11 minus 1? Is that prime? Well, 2 to the 11 minus 1 is equal to 2,047. And actually, 2047 is equal to 23 times 89. That is not prime, which is very sad. However, on the bright side, we can show something quite interesting about the Mersenne primes, and that is they require a prime exponent to be prime. That's kind of why we were seeing that pattern there. If a Mersenne number has a composite exponent, then it is immediately composite, and that rules out that number from being a Mersenne prime. To do so, we will use the formula that x to the n minus 1 is equal to x minus 1 times the geometric series on the right, right over here. You can see that this works by kind of foiling it out, and you see that the first term of this kind of expansion cancels with the second term of this expansion, and so forth. So if you consider a Mersenne number of the form 2 to the ab minus 1, where a and b are both greater than 1, so that ab is a composite number, if we let 2 to the a be x, then we get that 2 to the ab minus 1 actually equals x to the b minus 1, which should look familiar because it's part of that formula on the top. And that means x to the b minus 1 and hence to the ab minus 1 equals that product of two integers, which of course can't be prime. And thus, if a number n is composite, then 2 to the n minus 1 is not prime. But who cares, right? Why care about the Mersenne primes? They just seem like a special case of the prime numbers. So what's so special about them other than they're sometimes slightly interesting properties? Well, consider the problem of checking if a number is prime. How would you test if 97 is prime? Well, a common method is to basically check all the primes below it and see if they divide it, and if they don't, then it has to be prime, right? And a very systematic way to do this is with a sieve, or with the sieve method. So what you do is you list the first, let's say 100, because 97 is less than 100, and you cross out 1 because that's never prime, right? Just by definition. And then you circle the first prime that hasn't been, or the first number that hasn't been crossed out yet, or so that's 2, and you cross out all of its multiples because 2 is prime, so you gotta cross out all those because they can't be prime anymore. You do this, and then you continue on with 3. That's the next number that hasn't been circled or crossed. You do the same, you cross out all of its multiples that haven't been crossed out yet. And you continue with 5 and 7. And then you stop once you get to 11, because 11 squared is actually greater than 100, right? 121 is greater than 100. And so it actually can't eliminate any more numbers from this list, and so you can circle the remaining numbers. And those are all prime, and you can see 97 is prime. That's all fine and dandy, but then the question arises, well, how would you do it with a much larger number, like this 20-digit number I listed? And it turns out that number actually is prime, but it would be very difficult to test using the sieve method. It turns out the algorithmic complexity of this sieve is n log n, which is close to the number itself. And so if you have numbers that are millions of digits long, or it would be almost impossible for a computer to handle performing a sieve with those numbers. But as it turns out, the Mersenne primes can be tested for primality in a much less computationally demanding way through the Lucas-Lehmer test. So if you define a function recursively as follows, you let the first term of a sequence be 4, and then all the terms after that are the previous term squared minus 2. So you get, you start with 4, and then the next one will be 4 squared, 16, minus 2, that's 14, and so forth. 14 squared is 196, minus 2 is 194. You see those numbers go quite quickly, but as it turns out, a Mersenne number, 2 to the p minus 1, is prime if and only if you go to the sequence, you look at the p minus 2 place, you take that Lucas sequence number, and if that Mersenne number divides that Lucas sequence number, then it turns out that that Mersenne number is actually a prime. And so what a computer can do is it can perform this test using modular arithmetic, squaring a number and then reducing it and so forth. And it can check if a Mersenne number of the form 2 to the p minus 1 is prime with an algorithmic, or with basically p steps, which is much better than n log n. However, it's still quite difficult, right, to do so as you get to like millions of digits long. And so when you're searching for larger and larger prime numbers, right, it's much easier than the sieve method. So as it turns out, the 5 largest known primes are actually all Mersenne primes because they're easy to check primality, right? But again, right, it's still enormously difficult. 2 to the 82,589,933 minus 1, that is an enormously large number. It's still going to take a computer forever to check. So, as it turns out, there is an organization called the GIMPS, which is dedicated to searching for larger and larger Mersenne primes. And what they do is they take volunteers who are willing to lend their computational power, and those volunteers download the GIMPS software in their computers. And when their computer is idling, the GIMPS software basically boots up and starts basically running the computations to check if these numbers are prime. And if you download this software, you might be lucky enough that your computer actually finishes one of those computations and discovers a new Mersenne prime. And this one at the top was discovered by a lucky fella in Florida, just some random guy, which is pretty fun. Okay, now the perfect numbers are numbers which are equal to the sum of their proper factors. So here are some examples. 6 is equal to 1 plus 2 plus 3, and its factors are 1, 2, and 3. And 28, its factors are 1, 2, 4, 7, and 14, and it equals the sum of those numbers, which is just kind of fun. It's interesting. Now, a thing you might be asking is, well, what about in 6's case? What about 6? 6 is a factor of 6. Well, as it turns out, 6 is not a proper factor of 6, because a proper factor is all the factors not including itself. But alternatively, you can define a perfect number as a number which is equal to half the sum of its factors, its normal factors. So 6 is equal to half of the sum here, which is 12. Now, it turns out the perfect numbers are actually intricately connected to the Mersenne primes. if you list out the first 5 perfect numbers, you might see a pattern here. All the perfect numbers are a product of a Mersenne prime, 3, 7, 31, 127, and so forth. Those are Mersenne primes, and a power of 2 on the right. So if you write them out like this, you might see a pattern between those Mersenne primes and the specific power of 2. So I'll give you maybe 20 seconds to see if you can notice that. Well, as it turns out, the power or the exponent of the Mersenne prime is always 1 greater than the exponent of the power of 2. So 2 is 1 more than 1, 3 is 1 more than 2, 7 is 1 more than 6, and so on. And why does this work is what you might be asking, which is a very natural question. So if you consider a Mersenne prime of the form 2 to the p minus 1, where p is a prime, and you let it be q, then q times 2 to the p minus 1, so that is 2 raised to the power of p minus 1, has factors, has the following factors. So you can kind of consider the factors that don't involve q. So those are just the powers of 2 up to 2 to the p minus 1. And the ones that do involve q, which are those factors at the top here, but just multiplied by q. And so the sum of those factors will be q plus 1 times this sum right here, the sum of those powers of 2, like so. And q plus 1, of course, is 2 to the p, because q is that Mersenne prime. And then the geometric series sums actually to 2 to the p minus 1. And if you, as you can see, 2 to the p minus 1 is actually the Mersenne prime itself, q. And so we get that this is actually equal to twice the original number, which is how we define the perfect numbers at the beginning there. So those are perfect numbers, but that's about all we know about the perfect numbers. There are actually 2 very important open questions pertaining to the perfect numbers that we have been unable to answer for thousands of years. And they're actually quite simple to understand, but they're very difficult to prove or to come up with an answer with. So the first one is, are there infinitely many Mersenne primes? And consequently, because each Mersenne prime has its respective perfect number, are there infinitely many perfect numbers? And we have no idea. Yeah, it's been an open question since the Greeks, and yeah, we've still made very little progress into this problem. So that is something you can think about and consider. And the next one is, do any odd perfect numbers exist, right? Because all of the perfect numbers we saw were a product of a Mersenne prime and a power of 2. And a power of 2, of course, makes that product even. And so the question is, well, do any odd perfect numbers exist? We know that if one does exist, it has to be enormously large. And it has to have like something like 75 factors or something, or 75 different prime factors. But again, yeah, we have made very little progress other than that into this problem, and it's very simple to state, but it's very difficult to make any headway into. But it's just a fun question to think about. Well, that is my presentation on the Mersenne primes and the perfect numbers. So if you have any questions, please let me know. And if you're interested, that is the 16th Mersenne prime. That's 2 to the 2203 minus 1, and it's got that many digits, which is pretty wild to think about.